Okay, so I don't remember where we left off last time, but this is day 2 of the review, the second and final day of the review of MA343. And so, like I said last time, we won't go through every single one of these. We don't have that much time. But one thing I forgot to say last time was look through there between Wednesday and Friday and see the ones that you read and go, I have no idea what that means. Then let's do those, right? But so if you see one or you did that on your own, then let's focus on those. Some of these are just terminology and vocabulary kind of stuff, and it's important, obviously, but I'm not going to test a lot of vocabulary stuff, particularly from MA340. There may be vocabulary stuff from the new class, but mostly I want to focus on working on problems where you have to do some kind of calculations or things like that. One thing I want to make sure that I get to today is the concept of hypothesis testing, confidence intervals, and elementary linear regression. Right? Those are the main things from MA340 that we're going to start in on, and it's going to be assumed that you know what I mean when I say a hypothesis test or a p-value or those kind of things. Right? So this one, not this one. This one, but before I get to that one, I've highlighted for you to do this number 24. And this, what is this called when you have counts in a cross tabulation? It's called a contingency table. All right? But this is actually a chapter 9 problem in our new book. And that's where we're going to start. So even though we did this in MA340, chi-square tests and contingency tables, that's the one chapter I'm going to overlap with MA340. So we're going to redo this, but I still want you to do this problem. But let's talk about it a little bit of what I'm expecting you to do here. The first part says create a side-by-side bar graph that compares the 3 seat positions with respect to nausea. Right? What is a side-by-side bar graph? What does that mean, side-by-side?
So you put like front and you have nausea or no nausea, like that.
Okay, exactly. You're going to make a bar graph. Think of these as being groups. The group of people who sit in the front, sit in the middle, sit in the rear. So with this group, what percent had nausea, what percent didn't? And then for this group, and then put them side by side. Right? There's 2 different ways to organize it. Either one is fine. It's kind of a matter of personal preference. But you could go front, middle, and rear, and then have a nausea, no nausea bar, right? That's percent or count, but percents I would highly recommend. And then for middle, and then for rear, something like that. I'm making up the heights of these bars, but that's one way of doing a side-by-side bar graph. Another is completely separate graphs, but then they're stacked up next to each other. You could also organize this by nausea and no nausea, and then a bar for front, middle, and rear. Right? How many got nauseous if they were in the different locations? So either way of organizing it. It's basically row variable or column variable as your grouping variable down here. Right? But what do you need to compute to get the heights of those bars? Percentages, right? And they're called conditional percentages. Conditional on, what does that mean? Conditional.
Like if you're in front, then what's percent nausea?
Exactly. So if I sum all 6 cells in this contingency table, I get the grand total that were in this study. right? Well, if I take 58 and divide by that grand total, then that tells me what percent out of the whole sample did two things. They sat in the front of the bus and they got sick. Right? That's not what I'm interested in for that. I'm interested in if you sit in the front. So that's a conditional statement. Among those who sat, or if they sat in the front, what percent? So now you look only at that first row. Sum this first row, get a total out here, and then take 58, divide by that total. You have the conditional proportion who got sick if they sat in the front of the bus. Understand? And then that's what you're going to graph. And then part B just says summarize the results. So basically it's tell me what you see when you look at your graph. And really C is the same thing, kind of, okay, tell me what you see, and then is there an association? Well, the chi-square test that you learned probably right at the end of your MA343 class, we're also going to learn in Chapter 9 of this book, gives you a formal statistical hypothesis test to answer this. That's not what I'm after here. Just look at the picture, do the eyeball test. I see an association or I don't, and explain why. What it is you're looking at that makes it look like, yeah, there's an association. What does that term, this is review, what does that term association even mean in a statistical sense?
It's dependent or independent.
Okay, they're either dependent or independent. So if there's an association, then whether or not you get sick depends on where you sit. So if there is an association, what do you expect to see?
A different proportion of people getting sick in each area.
Exactly, a different proportion. Now probably, if we look at these numbers, it looks to me like more people are getting sick sitting in the back than those sitting in the front. So it looks like there's an increase in nausea, right? But look at your graph and see if that plays out. But if there's no association, then the percentage in each of those three rows would be roughly the same. Right? So that's all we're asking for there when we say association. Just the eyeball test. No need to do a formal statistical test of that. It just wasn't for you?
Yeah.
Okay, because I went back and I looked, and I thought, I don't know what he's talking about, because I see it, but it may be the Apple thing that you were talking about. Okay, so this one, number 25, says construct a scatter plot, right, to show how percentage of ash depends on the density of a coal particle. So this data, we've got a chunk of rock, right? And we're going to measure two things on that chunk of rock. How dense it is and what percentage of it is ash, right? So we form an ordered pair out of those two observations, right? An x variable and a y variable, and then form a scatter plot. Which variable is the x-axis and which variable is the y-axis?
Density is X, percent of ash.
Okay. Density is x and percent of ash is y. Why is that?
It's because...
Is it because of the order they're put in?
No.
No.
Percent of ash is...
Good. It says here, percent of ash depends on the density. The dependent variable is always y. It's the one you use the x variable to try to predict the y variable. So what's the x variable called?
Explanatory.
It's called the independent variable, also called the explanatory variable. And it's x for explanatory. Don't worry about what it starts with. Okay? So everybody understand how to do a scatter plot? Right. Now, when you do these things, for this worksheet, it's okay just to do it by hand, right? Later, not very much later, but within the next couple of weeks, we're going to start using software to do that. You could do it with Microsoft Excel pretty easily, right? You just copy these numbers into Excel, and and insert a graph and ask for a scatter plot, and it's pretty easy to get, right? So we'll practice with that a little bit, but we can also use SAS to do it. You can also, if you have your TI-83 or 84 left over from your MA343 class, then it'll do scatter plots also. And it will do the rest of this, where you need to compute the correlation coefficient and the regression line and all that stuff. Right? How many people still have that calculator?
The same one now. Getting a new one arrived in the mail today.
Okay. So everybody raised their hand. So even on a test, I can give you a question that will require you to use your TI-83 or 84. Right? It's not required for this class, so if somebody didn't raise their hand, then I'd have to rework that. But
Well, I was going to give mine to my brother, so.
nope, too late. You raised your hand. So how do you compute the correlation coefficient, get the equation of the regression line using your calculator?
And put it into L1 and L2 and then run
Okay.
4 stacks on L1.
I'll tell you what, let me do this. I can remember not to write on this with the although it's dry erase, it should come off, but I forgot what I was doing. Oh yeah, put X into L1, right? Remember this? You got a list editor, and you have L1, L2, L3, all that. Put your X variable into L1. Put your Y variable into L2. Then once they're entered, do you remember where you go to do it? Those that just had it last semester probably remember, but okay, you push the stat button. Then go over to tests, and then you go down to lin-reg t-test. Okay? Now, short of doing that, if you had to do it the long way, there are formulas to compute the slope and the intercept of a regression line based on summary statistics and the correlation from that. But you have to have the correlation. This will also give you the correlation. Right? Correlation is really hard to get by hand using a formula. It's a pretty nasty, ugly formula. We'll do that formula when we get to chapter 10, but for now I'm not looking for you to have to do that. So this is good enough to get the equation of that line. Okay, so that'll give you the correlation coefficient. And what's that? Oh, I even put it there. R. Start saying, what's it called on your cat? It's R. Right? So R, then give the equation of the regression line. Your calculator will give you a value for A and a value for B. So then you form the equation as it's written here, A plus BX. And A is called the intercept, the y-intercept, right? And B is the slope. Okay? So spoken like good mathematicians. Now say it like a statistician. What do we mean by the intercept? We got density and we got percent ash.
So how dense it is if the percent of ash is 0.
Right. Well, it's the other way around.
Yeah, flip
right?
that.
It's the percent ash is our y variable. So it's the percent ash we would predict if the density is 0. Now, in that case, and in a lot of cases, it doesn't make sense to say when x is 0. You can't have a coal particle with 0 density. Right? Like helium or something. I don't know, but that's the interpretation of it. Now, what's the slope?
Change that there is in ash according to the density for 1.
Yeah, exactly. So it's the change in whatever your y variable is, in this case percent ash, per unit change in x. Now in this particular data set, look at x. It starts, these are in order. They wouldn't have to be, but they happen to be. 1.25, quit doing that, to 1.55. I never have a 1 unit change in x. I don't even quite have a 0.5 unit change in x. But that's still the interpretation of that number that the calculator is going to give you for b. It's the amount of change you expect for a 1 unit change in that x variable. It'll be some number that's big. If I remember right, it's like 73 or something like that. So a 73% change in this. Well, for a 0.5, not even a 0.3 change, you go from 2 to 23. So for a whole unit, you go 70-some. Proportional reduction in error. Proportional reduction in error we get by using the regression line to make predictions instead of simply the mean y bar. What? That's r squared. Right? That's r squared. Another way you'll hear that said, actually more commonly than this way, but this was written based off of our old textbook, is to say it's the percent of the variability in the y variable that can be explained by the x variable. And that's r squared. If you take the correlation coefficient and you square it, that's the interpretation of it. It tells you what percent of the variability in percent ash can be explained by knowing the density of the rock. And then predicted values, you probably can figure out how to do predicted value once you have the regression equation. Right? What do we mean by residual? Same thing we mean by error. Error and residual are the same thing. What is that? The difference between the predicted and the actual. So if I look at a scatter plot, and I fit a line up through there, that line predicts every point. For any x value, I plug it into the equation, I get a point that's exactly on that line. That's my predicted value. The actual value for, say, this one is that far off the line vertically. The distance of that vertical line is the residual, or the error in the prediction. So when they ask you for the residual, you first get the predicted value, then you go back and see what the actual value was for that x, and just take the difference. Okay? All right, so that finishes up the exam 1 thing. Let's look at exam 2. Bunch of vocabulary here. Let me read them real quick. There's a lot of stuff in here about design of the experiment, which is an incredibly important topic in the field of statistics. Unfortunately, by starting this class in Chapter 9, it's already been done. So you did all that in MA343, but just remember there's a lot of discussion about bias in studies and proper design of study and all that kind of stuff. You need to be aware of those things when you get data to analyze. You need to assess, well, was this data collected in a statistically valid way? If not, my inference won't make any sense. Right? So that's what a lot of this stuff is about. What's the difference between an observational study and a experimental study?
Observational just collects the data. Like experimental, like they actually plan and they control group basically. Like they're going to do this increase to this group and they're going to compare it to the other one.
Okay. So if I'm interested in studying how your test scores on statistics exams depend on the number of hours that you study for that exam, I can do that with an observational study by just giving you a survey right before the exam. Hey, how many hours did you study for this exam? And you estimate for me. If I wanted to do it as an experiment, what would I have to do? I would have to assign a certain number of hours to each student. So Emily, I'm sorry, you only get to study 1 hour. Nate, you're 0. You got to come in cold, buddy.
Gotcha.
Right? So you can't always do experiments. It doesn't make sense. But if you can, it's a better type of study design if you can do an experiment. In a regression setting, it's almost always observational. It's hard to control that X variable for most cases, like the coal example we were just doing. We don't get to control the density of the rock. We just go collect rocks and, oh, look, this one has a certain density. But that's observational. Okay, in this exam review, ooh, that's ugly, are some probability problems. So I do want to review a little bit about some probability rules. We won't do much with it in this class, but there are some, let's see, I think that was a new page, right? There are some of the rules that we will need to know, particularly conditional probabilities. A lot of the things that we will do to compute p-values and things like that will depend on conditional probabilities. So what does that mean, conditional probability?
What's the probability given certain conditions?
Given certain conditions, right, exactly. So we write it like the probability that event A occurs given event B has occurred. So that vertical line means conditional upon. So a minute ago we were doing the bus nausea data and we computed conditional proportions. It's exactly the same thing, right? We say, given that they sat in the front of the bus, what was the probability they got nauseous? Do you remember what the rule is for computing conditional probability? Okay, say the words. The probability of A,
Plus the probability of B.
not plus the probability, and. Probability of A and B both occurring divided by the probability that B occurred. So it's the dividing by this probability which is computing a conditional proportion. In our contingency table with the bus data, they weren't probabilities, they were counts, but it was the same thing. How many people both sat in the front and got sick? Oh, I said it backwards. So I'm conditioning on sitting in the front. So B is sitting in the front. A is getting sick, right? So they get sick and they sat in the front. I remember the number was a 58. But I don't remember the other numbers, so we can't compute it without going back. But they got sick and they sat in the front, but then divided by the probability that they sat in the front. So that's computing that row percentage, not the percentage to the grand total, saying they had to meet this condition first. So you can do it with counts, or you can do it with probabilities. If I convert those probabilities, I get exactly the same answer. Okay? If I multiply through both sides of this equation by the thing on the bottom here, I see that I get what's called the, anybody remember what this rule is called? Probability of A and B is equal to the probability of A given B occurred times the probability that B occurs. What's that called? What's that? No, it's not. It's not Bayes' theorem. Bayes' theorem is related to this, but this is the multiplication rule. Right? Now, if A and B happen to be independent events, so it doesn't matter where you sit in the bus, the same percentage get sick wherever they sit, then conditioning on B doesn't affect the probability of A because they're independent. So this would just be probability of A times the probability of B. So if they're independent events, then you just multiply the two probabilities together. But to allow for them to possibly be dependent, you condition on one happening, and then what's the probability of the other one happening given that thing happened. So one more rule that we won't use it a whole lot, but if we use the word or instead of the word and.
It's probability of A plus probability of B minus probability of A and B.
Good. Now, I don't tend to write it out because it's just using cumbersome notation, but sometimes you'll see it written as an intersection symbol, right? You're mathematicians, so you know what that means, right? Or a union symbol. The word and means intersection. The word or means union. So A union B is A plus B minus A intersection B. Now, why is this piece on here?
You don't want to count twice for A.
Exactly. So, back to my bus where you sit and get sick, the probability you get sick or you sit in the front. If I put the word or in between there, then if we go back to that contingency table, somewhere right there, the probability you sit in the front or you get sick, well, sitting in the front are all of these people, 870 plus 58. That many sat in the front. And then 58 plus 166 plus 193 got sick. So I can't just add the number who got sick to the number who got, I did it backwards, the number who got sick to the number who sat in the front and be done, because what happens with these 58 people? They're in both of those totals. They've been counted twice. So you subtract them off once to offset having double counted them. That's why this term is here. Okay. So those are the main three rules that we have for probability that you need to remember. You also need to remember, probably even more importantly, how to compute normal distribution probabilities. Let's find one of those. Here's one. So number 20 says, serum cholesterol is an important risk factor for coronary disease. The level of serum cholesterol is approximately normal with a mean of 219 and a standard deviation of 50. Then it talks about being less than 200 and being over 250 is at risk for heart disease. What is the probability that a randomly selected person will have borderline, which means they're greater than 200, but they're less than 250? Right. How in the heck do I compute that probability? It says, what is the probability? This is a probability problem. How do you compute that?
Probability that they're less than 250 minus the probability that they're less than 200.
Okay, you could do it that way. Now, how do you compute those probabilities?
Calculator or?
This is a normal probability problem. How do I know that? Because it says approximately normally distributed. So if you have a TI-83 or a TI-84, it's easy because you have a function built in there to do normal probabilities. If you don't, you've got to use a normal table in the back of the book and compute z-scores and all that stuff. So since you all have that calculator, I don't have to teach you how to use the table in the back of the book. But I do want to remind you how to do z-scores. Do you remember what a z-score is?
Standard deviation.
Okay. So a z-score is a standardized score. So if you take somebody's cholesterol, you can standardize it. Well, remember last time we did the empirical rule and we talked about if they're plus or minus 1 standard deviation, plus or minus 2 standard deviation. A z-score is how many standard deviations they are from the mean. So z-score is number of standard deviations from the mean. Okay? So in this problem, our two boundaries are 200 and 250. So let's see, what would the z-score be for 250? So I'll call it the upper z. How would I compute z-scores? Do you remember?
250 minus.
Okay, the value of interest, which is 250, minus the mean over the standard deviation. Now I'm using Greek letters, which means population parameters. Mu for population mean, sigma for population standard deviation. And I'm using that because that's the way they gave it to me. They said cholesterol has a mean of 219. It doesn't say in a sample we found a mean of 219. They said it as if it's the whole population. But I could just as easily replace the mu and the sigma with x bar and sx. And it's still called a z-score. So 250 minus 219 over, what is it? I can't remember. 50? That would be the z-score for the upper limit. Right? But with our calculator, we don't really have to do that. What we want is the probability that a randomly selected person, call their cholesterol level X, is between 200 and 250. Oh man, where is this in my calculator? Anybody remember? Good. You push the second function button and then the vars button. And above the vars button is DISTR, which is short for distribution. So any time you have some kind of a distribution you're supposed to deal with, normal, binomial, F distribution, T distribution, they're all in that button, right, under that button. So find the normal CDF function, and then you enter the left bound of the region you want, the right bound, the mean, and the standard deviation. So it would be 200 to 250 with a mean of 219 and a standard deviation of 50. Now if you have the older style calculator, this is how you would enter it. If you have a newer style, it's going to say lower and upper. Does anybody have the newer one? What is it? What are the words that it uses?
Lower, upper.
Okay, lower, upper, mean, standard deviation. Okay? So if you have the older style, you have to remember the order that you're supposed to put things in. It goes lower, upper, mean, standard deviation.
All the 84 should have it. If you don't, you just have to update your calculator.
Yeah, if you have an older 84 like the one I have, it's like this. But you can go to the website and download and upgrade the memory of it to have the new version. But it's not critical that you do that. Yeah. Okay? Now, this question doesn't have it, but the one that I've assigned to you to do does, where it asks a question, what is the 95th percentile? Or find numbers such that so much percent is between. What function do you use to do those? The inverse norm function. So normal CDF is like the second one down on the list, and inverse norm is the third one down on the list. So here they gave us values for cholesterol and asked for a percentage or a probability. If I ask for a percentile, then I'm going the other way. I'm doing the inverse of that. They give me a percentage and say what value has this. So what percentage of people, or what cholesterol has 95% of people below it? Some question like that. Right? So you would use the inverse norm function. So what is, let's go back to this one. Is that the right one? That's not the right one. Yeah, it is right there. What is the 95th percentile which we can label P95? What's the 95th percentile of cholesterol? How do I compute that?
0.25.
Okay, I go to the inverse norm function by pushing the second function, then the vars button, going down to inverse norm, which is the third thing down, inverse norm, and then whatever percentage of the distribution you want to be below the value you're after. Well, the definition of percentile is it's a value that has this percent below it. So inverse norm of 0.95 with a mean of 219 and a standard deviation of 50. So it's area to the left, mean, standard deviation. All right? Everybody good on that? We'll do a lot of stuff with normal distribution and t-distribution and those kind of things this semester. So knowing how to use these functions is going to be important, but actually a lot of times the software is going to produce them for us as part of the analysis. So we kind of get beyond needing to use the calculator to do a lot of this. And we'll use Excel or we'll use SAS to do it. So. But I want you to understand what's going on behind the scenes. So important that you learn those. Number 24 says the online access. You got a question?
Yeah, on 23C, when I was taking a look at it, you said find the number x. Are you meaning one value or two values?
Yeah, this is find a value x such that 0.15 minus x and 0.15 plus x. So basically I'm saying find the z-score. How far do you have to go on each side of the mean to get a certain percentage in the middle? Right? So it could have been, think of it as, I wish I could write on this, but this is left or lower and this is upper. Find those two values. From that you can solve what x is. But
You just want 5% on each side.
right. We want 90% total. So if I go, let's do it with the cholesterol data instead of that problem, since you're supposed to work it on your own. I've got a normal distribution. It's centered at 219, and it says we want 90%. I want two values such that 90% falls between those two values. So just eyeballing it, 90% of that area under that curve looks like it's about there. So I'm going to call this L for left, this R for right, or I could use lower, upper, or whatever. If I want 90% or 0.90 to be in the middle, how much is not in the middle? 0.1, right? Total area under the curve, by definition, has to be 100% of the probability, or 1. Right? Proportion is 1. So if 0.9 is between those two numbers, then that leaves 0.1 left over. Half of that's going to be down here, and half of that's going to be up here. So if I want to know what L is, what do I do in my calculator? The inverse norm, just like this, only instead of 0.95, what do I enter right there? What'd you say? 0.05. Area to the left. So the left of my L is 0.05. What would I enter for R? 0.95. The total area to the left. You don't enter 0.9 because that only gets me down to L. I got to go all the way to negative infinity, or it's cholesterol, so 0, right? So I add those two numbers together. So we're back to the 0.95. Now, the one that it asks, it says find a number x, so that you would have 219 minus x and 219 plus x. Well, now that you know what L is and R is, you can solve for x. Right? So, do it for me. Do what L is. Somebody has their calculator, right?
Oh, it's 136.7.
136.7. If you can't match that number, raise your hand and we'll figure out what's going on. But 136.7. Right? Does that look right? Just looking at the data?
Yeah.
Well, standard deviation is 50. Where does one standard deviation fall?
219.
Okay, but on this graph, where's one standard deviation fall? Halfway down the hill, right? So halfway down the hill is about right there. So take 219 minus 50 and you get 169. Okay, so 136, yeah, looks right. So now I know what L is, solve for x. So 219 minus x is 136.7. Solve for x. Right? And then if you add that same x to 219, you'll get the same number you get for r if you put that 0.95 in there. Right? So the reason I worded the question that way was at the time we were talking about this whole idea of empirical rule and add and subtract the same thing. So I want to know what is that thing you add and subtract to get you 90%. Right? Okay, let's hurry because I'm running out of time. There's some questions on here. I didn't highlight any of them, but they're fun questions. They're probability stuff, but we really don't need it for this class. You did it in MA343, but we need to talk about hypothesis testing and p-values and confidence intervals. So, in a hypothesis test, you have a null hypothesis and an alternative hypothesis. Remember that? And the null hypothesis, what does the word null mean?
One you're assuming to be true. Testing if it's true. Sorry.
Okay, but the word null,
Not void.
it means none or not or, right? So the null hypothesis is generally what you're hoping to disprove, right? Like if I'm comparing two drugs, my null would be there's no difference. I'm hoping to prove there is a difference, right? So hypothesis test, it says, hypothesis test, the probability of seeing a result from a random sample at least as extreme as the one you got from your random sample. It's going to be one of these values. So you need to know the definitions of these things to figure out which that is, right? It's highlighted, so I'm not going to tell you the answer. You can look it up. But what is a confidence interval? What does that term even mean? A confidence interval.
You're however confident that the mean lies within two values, or the
Okay.
testing lies within two.
The mean of what? Of the whole population, right? So you've taken some sample data, and if you can do means, you can do proportions, you can do any parameter. But if we talk about means, a confidence interval for mu, which is a population parameter, is going to be a sample estimate of mu. So x bar is the sample mean. We're going to use the sample mean to make inference about the population mean. So I take the sample mean as my best estimate. But I know it isn't going to be exactly right. Right? I know that the mean from my sample isn't going to get the mean population exactly right to 1,000,000 decimal places. So I add and subtract a fudge factor. That's what engineers call it. Statisticians call it margin of error. Right? The margin of error. And how do I compute margins of error? I'm not sure how to say that. You need a standard error, and you need
Well, your T score.
a T critical value or a Z critical value. You need, and what do we mean by critical value?
Someone who passes that threshold, your peak value.
We basically need this. How many standard deviations or standard errors we need to go in order to have a certain degree of confidence, right? So I'll just say critical value. Well, since I'm specific to a mean here, that would be a T critical value. Remember that for means, we use a T distribution. For proportions, we use a Z distribution. Right? We'll flip back and forth between T's and Z's and chi-squares and things as we go through the semester, but this is review from before. So for a mean, it was a T critical value times the standard error of X bar. So I'll write that like this. SE for standard error. All right? What is the standard error of X bar? Remember this little thing we had called the central limit theorem? What does the central limit theorem say the standard error of a sample mean is?
The same thing as the standard deviation of the population.
It's not the same as the standard deviation of the population. It has the standard deviation of the population in it, but
Is that divided by the number?
it's the standard deviation of the population
Square root of n.
divided by the square root of n. Right? So the standard amount of error in your sample estimate depends on how big your sample was. The bigger your sample, the less error. Because the bottom of the fraction gets bigger, the value of the fraction gets smaller. Right? And I'm out of time, so we're going to quit there. While you're packing